Okay, hello. We're going to talk about activation energy and the Arrhenius equation. And in this first problem, it's a pretty straightforward one. We're looking at how we can find the activation energy for the reverse reaction. What we want to do is sketch a little energy profile diagram. So what this looks like is energy on the y-axis, and then we have kind of the reaction happening this way. So reactants, we can just kind of draw an arbitrary line. Here's your reactants, and then your products can be maybe like in different options, same energy, higher energy, lower energy. And what would determine that? Well, if you think about thermodynamics, the delta E of the reaction is basically the energy of the products minus the energy of the reactants. That number here is 45. So this is like an endothermic reaction. So if this is positive, what's going to have more energy, products or reactants? And that would have to be the products. So we have a case where we're going to have this and this. We have a line extending here. Then this would be our overall energy change, which would be 45, right? And so you can think about exothermic would be like downhill. You kind of would drop down. Endothermic is going to be an uphill reaction. The activation energy is always the energy from where you're starting to get over the peak. So we're going to start from reactants, and this is abbreviated as E sub A for activation energy. That's 60. So then in the reverse direction, starting from the products, if I'm going backwards, I don't have to like redraw a new diagram. Just think about going backwards. You're going to have to get over this barrier. So this would be your activation energy in reverse. And we can just do a little subtraction. That would be 15 kilojoules per mole. So note that if you switch a reaction, like reverse it, the delta E definitely will change signs, but activation energy is always a positive number. So you can't say that if you switch a reaction, the activation energy just becomes like negative 60. It doesn't work like that. It's always positive. Again, it's just how much energy you need to get over the top of that diagram. Okay, so make sure you can do that. And moving on, here's some more diagrams to look at. So one thing I guess we can break down is see if like this helps us. This is an endothermic reaction. That would again be like the kind of the products to reactants. These are all endothermic, so that doesn't help us eliminate anything, but nonetheless good to look at. So then the next thing would be we have a catalyst dashed line. Without a catalyst dashed line, with a catalyst solid line. So catalyst, something that speeds up the rate of the reaction. The way it does that is it does that by decreasing the activation energy. And we can look at these more in mechanisms in the next video. But generally, it's kind of like if you're going over a mountain, notice sometimes like with roads or like, railroads and, train tracks, like they have blasted tunnels through mountains. So that's, quicker and easier than going over the mountain. It's a big one. So the same way that the catalyst kind of like tunnels this hole through the diagram to make it quicker. So the catalyst should be faster. That's the solid line. So this one here would make sense. So you'd want the solid line to be a lower activation energy than the, if we're comparing that to the dashed line, right? Okay, so is it A? Well, the difference between A, C, and D, they all have the catalyst diagram, going faster or less activation energy, but a catalyst does not change the delta E. So it actually doesn't change any of the thermodynamics about the reaction, like delta E, delta H, delta S, all that stuff, delta G. So if you see, oops, look at this part here, that's actually saying that the catalyst is changing the energy of the products of the reactants. So that's not going to be what actually happens. The reactants products have to be the same. Okay, so that makes sense. So rate constant, this can be easily confused with the question about what affects the rate. And let's start with the Arrhenius equation. So this is K equals A times E to the negative EA over RT. Just write this. Name's not too important, but we'll refer to this often. So rate constant, K, and there's three factors here. So we have one is this A factor, which is kind of a fuzzy definition and sometimes interpreted different ways, but A has to do with the nature of the reactants. So this is specifically like how often they're colliding, and if the reaction has to have a specific orientation that's needed. Oftentimes the molecules are colliding a lot, but they're not in the correct orientation that will result in a reaction. So maybe the orientation has to be a very specific angle. So of like 300 collisions, only one of them actually results in a reaction. Those kind of things are, again, dependent specifically on the type of reaction happening. Pretty complicated, a lot of like physical chemistry and looking at actual, maybe geometries and stuff. But in a short summary, like that A factor, if it's bigger, you're going to have a bigger K because it's proportional. Okay, so sometimes that's called the pre-exponential factor too, because it's kind of in front of this E term here. So the two things that we look at and often are comparing that are maybe more important in these problems are activation energy, right? So that's here, which we talked about, and that's pretty much like we saw in the graphs, like what a catalyst does, right? Lowers the activation energy, that makes the rate go faster, which means a bigger rate constant. And then temperature also is here. Again, R is a constant, it's not changing. So temperature, this makes sense, pretty intuitive. Higher temperature, faster rate, bigger rate constant. All kinds of examples of that, right? So, or colder, vice versa, colder temperature, slower rate, smaller K. So that's something that can keep in mind. One other way to look at this too is that we can note that when you're talking about the rate, right, then you have also the concentrations that can come in. So right now we're just talking about this, right? And like we said, the bigger K is a faster rate, smaller K is a slower rate. But there's actually, another thing that affects the rate, which is the concentrations. So these of reactants affect the rate, but not the rate constant, right? So these are independent, right? But they both affect the rate. So saying what affects the rate versus what affects the rate constant definitely are different questions. Hope that makes sense. Okay, so now with that Arrhenius equation, if you look on your information page, there's a couple other forms, but one that's often used in these kind of problems is this, where you kind of just do some math and get rid of the A factor since it's complicated and not that important to know about. Mainly what we want to, again, focus on is usually like activation energy, temperature effects. So pretty simple kind of problem. You'll find these where you can just basically say like, oh, here's the rate constant at some temperature. Here's another rate constant at another temperature, call it T2. Doesn't really matter which one's T1 or T2, as long as you have the appropriate rate constant that goes with that. And the temperatures have to be in Kelvin. That's important. But then it's just basically plugging in. So we can plug in these numbers. And then we have EA. R is our gas constant. We want to have it in joules, so we want to use like the 8.3 number, so it's in joules. And then again, T1 needs to be, or this is T2 actually. Sometimes this is written T1 minus T2, and then there'll be a negative here. So if there's a negative there, then it's T1, this is T2. If there's just like here, then it's T1, T2 first, and then T1 second. So just watch out for that. And again, putting those 24 degrees Celsius and 150 Celsius into Kelvin, we get those numbers. Solving it for activation energy, we get something that's going to be in joules per mole, which we can then obviously put into kilojoules, how it's normally written. Okay, so again, you should get a positive number. If you get a negative activation energy, probably flipped around the values of T1, T2 or something. You can't have that. All right, part B, another thing you can do with the same equation, and then you can just kind of like make K1 your X, and then this is going to be your T1, which would be 373 Kelvin, right? And then you can just use like the same K2 as before. Again, it doesn't really matter which one you want to call your unknown. So plugging that in. We can plug in our activation energy that we solved for in part A, just again making sure it's in joules because R is in joules. And then we have T2 in Kelvin and T1 in Kelvin. So solving that, and gives us 0.32, or I guess if you want to write it kind of like these are written, 3.2 times 10 to the negative 1. It would be the same units as these, which is 1 over molarity seconds. It's the same order of reaction, obviously. Same units for K. One thing you can use to check your answer is what's the relationship between temperature and rate constant? Well, if temperature increases, the rate constant always increases, or if temperature decreases, the rate constant decreases. So you can oftentimes use these to see if your answer makes sense. And this does. This is a smaller K than the K at the higher temperature. All right, last one. So we have a reaction. We are changing the activation energy by introducing a catalyst. So again, you notice that the catalyst is lowering the activation energy, right? From this value to this value. Calculate the ratio of the catalyzed rate to the uncatalyzed rate. So we want to get the rate of a catalyzed reaction over the rate of the uncatalyzed reaction. That's what we're trying to figure out, that ratio. So because rate is like K times A to X, whatever, you know, maybe there's two reactants here, it doesn't matter. The rate and the K are proportional. So that's what this little fish means. It's a proportional fish. So if, you know, again, as one goes up, the other one goes up, vice versa. That's nice because if you're doing ratio problems, proportionality is good. Even inverse proportionality is also useful because you can just flip it around. But this makes it so that you can write the ratio of the rates equals the same as the ratio of the rate constants. And because we have the Arrhenius equation, we can now say, okay, well, how can I express K? And this is where you can just go look on your information page. K is A times E to the negative EA. I'll just make a note, this is the catalyzed activation energy. And then the uncatalyzed K would just be the same thing, except you have the uncatalyzed activation energy. Because A is the same, again, we don't need to know what that is, cancels out. I guess there's probably a way to mathematically make this maybe simpler. I just kind of plugged in the numbers rather than trying to manipulate it mathematically. And again, just make sure that these are in joules because R is in joules. Temperature is 600 Kelvin. Okay, so that's going to be that. This is activation energy in joules. All right, so plug that in. Which one goes faster? Hopefully remember that catalyzed rate's always going to be faster. And it's quite a bit faster. The answer comes out to be like, 8 times 10 to the 10. That's what, like 80 billion times faster. This is hugely important with chemical reactions in chemistry, like making catalysts or finding catalyst reactions is a worthwhile pursuit. Biologically, immensely important. All the reactions in our body would be too slow to sustain life. So we have enzymes that work to make these reactions millions, billions of times faster, so that we can actually, get stuff done and do biochemistry at a normal, livable timescale. So really important, and this is how they work. All right, let me know if you have any questions and send me an email or something. Happy studying.